Okay, welcome to the Henstitute. This time we're going to take a look at kind of a classic physics MegaWork energy problem, which is with a roller coaster. So what I have pictured down here is I have a little roller coaster car that has a mass of 250 kilograms. It's starting at the top of this first hill, which is 50 meters above the ground. It's going to be taking off over the top of this hill at about 5 meters per second. It's going to travel down this particular hill. Actually, I'm just going to make this in pink, follow down this hill, then up to point A over here, and then go down another hill up to point B, and then down to the very bottom. C here is at the lowest, so the idea is there's no height above the ground that we have down here. So the general question is usually how fast is it going at point A, B, and C? That's kind of the classic question. Now to tackle this, I've got the MegaWork energy equation up here that we're going to be working with. No pun intended, actually pun intended. And we're going to first eliminate some stuff. Now, a regular roller coaster, like I showed in my little introduction video, does actually have some friction. That's why my little roller coaster cart on my Connects eventually didn't make it back to the chain that last time, and I pointed out that friction is going to do negative work. For us, let's assume that this is a frictionless roller coaster just to make this a little bit easier, because I want to look at what happens when you're on an incline later, and we're going to try to simplify things and not have friction on an incline. We could do those types of problems, but it just becomes more complicated. Plus, as you're going along these different sections here, what happens is your normal force changes, because when you're on this side, your normal force is in this direction. When you're down here, your normal force is up. When you're up here, your normal force is this way. So unfortunately, that normal force constantly changes, which makes friction very difficult to kind of work with. So I'm not going to have us have any friction. We'll just stick with it being frictionless. So therefore, we don't actually have any work being done on this roller coaster. We are not going to deal with the fact that there was work done to bring it up this first hill. I know there was work done during this, like I described in my previous video, but we're not going to have that. We're starting at the top of the first hill. Is there going to be a change in kinetic energy? Well, if I'm trying to find velocities at these different spots, is this velocity? What is this velocity? What is this velocity? Then of course I definitely have to deal with that. So yes, we will be keeping this. Is there a change in gravitational potential energy? Well, we're going to be changing heights, so I've got different heights here that we're going to actually be working with. So yes, we definitely have this also going on. And then last but not least, do I have any springs going on? I don't see any springs. There might be springs in the coaster itself, but nothing that it's going to hit against, nothing that's going to stretch or compress. So nope. That's gone. So let's use the power of the eraser. Bye-bye work. Bye-bye elastic potential energy. And we are done. Now notice that I have this equal to nothing. So I usually put a 0 over here to indicate that I actually have this equal to something. In essence, what this is going to kind of show me is I'm going to bring one of these over to the other side, is that my change in kinetic energy is going to be equal to the opposite of my change in gravitational potential energy. So now what I can do is I can actually put in my equation. So I've got 1/2 m, and this is going to be Vf squared minus Vi squared. There's my change in kinetic energy. And this is going to equal the opposite of my mass times gravity, and this is going to be my final height minus my initial height. So I'm going to leave this negative sign out front, but in essence, we can kind of do that. One of the first things I love about this is when you see this particular problem, notice when I write it like this, I have a mass sitting over here, I have a mass sitting over here. Therefore, I can divide by the masses, and by masses, they would actually cancel from this equation. So erase that mass, erase this mass. What that really means is it doesn't actually matter what the mass of this thing is. The mass of the cart is irrelevant in this problem. That's kind of a weird concept, but it's actually kind of a neat one. The next thing I always like to do, since I'm trying to find velocities here, is I'm going to take this 2, I'm going to multiply by 2 on both sides so that I bring the 2 over here and cancel out the 2 here so I don't have to worry about it. So now I have the 2 over to the other side, and this quantity right here is my initial velocity, so I know my initial, and then I'm just going to be plugging in my final. My initial height over here is given, that's our 50 meters, and then we kind of go from there. The cool part is, even though it's going to go from the first hill to point A, and then from point A to point B, and then from point B to point C, you don't actually have to constantly be changing your initial. We can leave this initial height as the 50 meters that it starts out at the first hill. And we can leave this initial velocity as the 5 meters per second because it could be the velocity at the first hill. We don't have to figure out what A is and B is and so forth. And then all we have to do is plug in what the final stuff is, and we can kind of work it from there. So here's kind of a couple of cool things about this. One, you notice that A is at the same height as the first hill. What that means is that the velocity at A, basically HF here, would be the same. It would also be 50. What's 50 minus 50? Well, that's 0. So that means the entire right side has to be 0. Well, the only way the right side can equal 0 is if the left side also equals 0. That means the final velocity would have to be 5. So to figure out this velocity here at point B, it's going to be 5 meters per second, actually 5.0, but we'll just leave it at 5. So I don't actually even have to calculate anything with that one. So that's kind of nice. Now your next instinct is, hey, B down here is at half of that height, so it should be going half as fast or something like that, or maybe twice as fast, but things like that. But what you're watching out for is you have to watch out for the square on your velocity here. So let's do point B here and see if we can figure this out. We're going to try to find the final velocity at B. So I've got VF squared minus this 5 squared. That's going to equal, let's put in everything on the right side. So we got a minus 2 times our 9.8 times, and my final height is half of this, so that's going to be 25 minus 50. So as I kind of work this out, the left side here is going to be VF squared minus 25, and then on the right side, we've got this negative sign is basically going to turn this around. So it's going to be 50 minus 25 or 25 minus 50. So it's going to be a 25 over here. So I'll write a 2 times our 9.8. And then this is just going to be 25. And now we're ready to finish solving this. So we need to grab our calculator and see what we can kind of figure out. Really what we're going to be doing is bringing this 25 over to the other side. So we're going to be adding this 25 here and adding a 25 on this side. And that's what VF squared would be. And then we just have to kind of solve it out. So 2 times 9.8 times 25. All of this part is 490. And then we're going to add to it that 25. So I get 515. And then square root that, and that should find the velocity at point B here. Let's place this little 0 here. And so I take the square root of this answer, and I get 22.6936, blah, 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 blah. So I'm just going to round this off to 23 meters per second. What you notice here, and this is going to be kind of a guesstimation here, is if you notice I cut the height in half, the velocity did not just plain double. It didn't go from 5 to 10. Now, it didn't actually do anything else specifically that we can see. It's somewhere between tripling and almost 5 times bigger. So it's somewhere between, or not tripling, but quadrupling. So it's almost 4 times bigger, to 5 times bigger, somewhere in between there. And so as I kind of look at this, if I was not worrying about any kind of initial velocity here, and I notice my squared here, and then just a plain h on the other side, we should get approximately a quadrupling whenever you drop your height by half. So if I go to half the height, I should be about 4 times bigger. That's a kind of a good estimate, but we can actually calculate it out. And then last but not least, we're going to take the height and all the way down to 0. We can work all this again and figure out what this velocity down here would be. Really all we would be doing is changing. This would no longer be 25. This would now be 50 in here. And then we could solve it out and get exactly how fast we're moving at point C. I'm not going to bother to calculate that. You could calculate that if you would like, but it's the same kind of setup as you're doing part B, except that this would end up being 50 instead of 25, but we'd still be adding 25 to it, and so we could calculate all that lovely stuff out and get a velocity down here that we could find. So this is a great little sample problem of using a roller coaster and also the MegaWork energy equation. Hope you enjoyed this edition of the Henstitute.